Newton's laws will generate a relationship at the end of their application. And that relationship could be used to answer the question, or it could be used to do more than answer the question. It could be used to tell you something that you perhaps didn't understand about the way in which this was related. What I want you to understand is, my goal is to teach you how to apply this series of steps. You guys who have had a physics course before have a way of solving these problems already. I'm presenting you with my way of solving these problems. Now, when we are done with the static sine problem, which is the first one we're going to do today, your paper is going to be filled with things. I would, if I were you, set a column up on the right or left side of your paper that has a dialogue of what you're doing. Because although you might have this set of steps written down someplace, and I'm going to provide you with a piece of paper that has all of these set of steps on it, like a cheat sheet, what I need you to understand is, what I write down here, when we're done, is just going to be a mess. You are going to need to be able to go back to your notes and understand how each one of these steps was applied to the problem. That will be best for you. So without further ado, the sine problem requires a sine, and so I tend to draw this the same way all the time. So let me recognize that this is a sine. And if you don't understand, imagine that you are in a shopping center or a strip mall where there's like the curb here and cars park over here. There's doors here, so a doorknob, right there. And there's an awning above you and a roof goes up like that. Imagine a sign positioned like that. Can you imagine that? So when you're walking along the strip mall, you could see signs for each of the stores that's in there. So that's kind of what I want you to imagine that this is. So I have two cables attached to the sign. So this is cable number 1, and this is cable number 2. Cable number 1 is at an angle of theta with the horizontal. Cable number 2 is perfectly horizontal. And the sign has a mass of m. Now, if you need to be guided by a question, meaning if you need something with a question mark in it to understand what this will look like in your homework, the question could be, find an expression for the tension in terms of the weight. That could be a question. Now, I'm not going to write that down here. I want to tell you that the procedure can be applied whether you have a question or not. I'm going to apply the procedure, and hopefully at the end, it will be useful in answering the question. But the procedure can only do one thing for me. It can only tell me the size of a force or tell me the acceleration. That's all the procedure can do. In fact, all the procedure will really do is generate a custom set of equations that match my problem. So we're going to go through the set of steps now. And the first step is to identify whether I believe this is a first law problem or a second law problem. And that decision is made by deciding whether our system is accelerating or is not accelerating. Notice I didn't say moving. It's whether it's accelerating or not accelerating. This problem is not accelerating. It's a statics problem. So net force equals 0. This is a first law problem. All right, so next, you have to draw a free body diagram. The drawing of a free body diagram, to me, is the most important thing that you do here. So I want you to understand that the free body diagram serves two different purposes. Purposes. We'll go with purposes. It serves two different purposes. The first is something that is graded by your AP graders, so I want you to be good at it. The second, I use the free body diagram extensively to solve problems. So my expectation is that you will draw one that will be graded, but that you will also be drawing one that you will use to work. Now for us, that'll be the same drawing. But on a test, you'll have a box where you have to draw your free body diagram. You'll probably draw one there, and you'll probably draw another one that you will use to solve your problem. That's what I'll expect to see on the test. Drawing a free body diagram, there are 3 things that you should be looking for in your diagram. Size of the arrows, directions of the arrows, and proper labeling. That's what I will be looking for. So, let's begin. I am just going to go through my series of forces and apply each force based on their definition. The arrows that I draw will be done in such a way that they will represent the size and direction of each vector. And I'm going to base all of their sizes on the first arrow, the weight. There's always the fundamental force of weight in almost every problem we ever have. So the first thing you want to probably do is draw an arrow that represents the weight. This arrow should be drawn straight downwards. And its length sets the scale for the rest of the drawing. So when you draw this one, be careful of the scale here. You draw too small and everything else is going to be tiny. You draw too big and it might overwhelm your diagram. Next, I ask myself if there's any surface in contact with the object that could apply a normal force. And no, there isn't. It's not resting on the ground or leaning against the wall or touching the ceiling. If there's no surface in contact, then there's no normal force. Remember, these forces have names, and their names are related to what is happening. There's no surface, so there's no normal force. There are, however, cables attached to the object, which means there are tension forces. And it's not arbitrary which one I should draw first. I should draw T1 first. And the reason is because I don't know how big to make the arrow for T2, but I have clues on how big to make the arrow for T1. And when I say I have clues, T1 is the only cable that pulls upwards. So the length of T1 should accommodate the weight of the object. And what I mean by that is I'm going to draw T1 long enough so that this portion of T1 is the same size as the weight. Like I said, the weight sets the scale for the rest. That seems to me to make T1 longer than the weight. It's the only way I can do that. It's the only way that T1 can pull up with the same amount of force as weight's pulling down. T2, on the other hand, has to also match something about T1. T1 pulls to the left, so T2 must be long enough to effectively balance by pulling to the right. So all that dialogue that I just gave about how I chose the sizes of the arrows, if you don't know to do that, it would be appropriate in your notes to give yourself some dialogue about how we chose the size of those arrows. Weight was chosen arbitrarily. I just picked the size. T1, its size was based on making sure it pulled up enough to balance the weight. And T2 was drawn ensuring that I balanced the problem left to right. I'm being guided by the fact that this problem is balanced. That's why we chose it. It was Newton's first law, so I need to see balance on the arrows. All right, any questions about this one so far? All right, I keep going through my list, but there's only resistive forces left. And since there's no normal force, there's no friction. There can only be friction if there's a normal force. And there's only a drag force if there's velocity, and there's no velocity. So there's no resistive forces here. We've exhausted our list of forces. This is our free body diagram. And quite frankly, this is all you would have to do if you were asked to draw a free body diagram. What we are going to do next is how we use the free body diagram to solve our problem. But this is the end of the part where I say draw a free body diagram. This is also where I would tell you, if you're going to solve the problem and you need a diagram, Make a new one that is used for solving the problem. Leave this one for grading. The next part is the part that's hard for students. You have to draw in a coordinate system. The coordinate system is supposed to be used to help you, and it's real simple. We only can do one-dimensional math. Our coordinate system is about figuring out how to break these up so they're all one-dimensional. So you should be guided by two basic priorities. This is not on the list up here. The two priorities are this. If the object is accelerating, line up one of the directions with the acceleration. It is the only way to solve the problem. If the object is accelerating, line up one of the directions with the direction of the acceleration. You'll not be able to solve the problem otherwise. If that's not an issue, then line up your coordinate system with the most number of forces possible. That's your second priority. Line up the coordinate system with the most number of forces possible. That's your second priority. Now, if you don't know what I mean by all of that, you're going to draw in X and Y. And if you do so correctly, you make your work easier. If you do so incorrectly, you make your work harder. So for those of you who are looking at me like you have no idea what I'm talking about, look, I could make this the X direction. And if I make that the X direction, then that has to be the Y direction. Now, this would be the stupidest thing to do. But X and Y have to be at a right angle to each other. And now that I've drawn in my coordinate system, any vector that's not lined up with one of the axes, I have to do trig on it. So you understand, I purposely chose an X and Y that would make this an impossible task. Because now every one of these forces has to be broken up into an X part and a Y part. So this is the absolute worst way to do this problem. I want to choose a method that makes my life easier. And already two of these vectors are at a right angle to each other. So let's use that knowledge to reduce the amount of work I have to do. There. I've chosen a coordinate system that will help me. That's not so terrible, but, and this is not written on the board, but this really is step C, right? A, B, C. A, draw the coordinate system in the direction of motion. B, draw the coordinate system so it lines up with the most vectors possible. C, any off-axis vectors must be converted to components. Any off-axis vectors must be converted to components. That means x's and y's. So, put my theta in there. Wrap a triangle around the angle. And do your sine and cosine stuff. Now, I no longer have patience for sine and cosine stuff. You should probably still have patience, but I don't. You're not going to see me writing opposite and adjacent and hypotenuse anymore, and sine, cosine, and tangent. You're going to see me say that this is T1 cosine theta. Why? Because it's on the adjacent side, so it's the cosine. And this one is T1 sine theta. If you can't do that, you need to make sure that you are figuring out why I wrote cosine and sine where I did. And you'll need to be good at it. So if you don't understand this, you should probably come and see me. But also, from this point forward, I'm done playing with trig. Look, cosine and sine are percentages. That's what they are. They're a number between 0 and 1. That is a percentage. So this tells me what percentage of T1 pulls to the left. And this tells me what percentage of T1 pulls up. That's what sine and cosine are doing here. But also, once I have found the components, I don't actually need the original vector. And although I will not expect you to do what I'm about to do, I do think it's worthwhile to understand that at this moment, my problem has just been turned into two one-dimensional problems where I have weight downwards, I have T1 sine theta upwards. And where I have T2 to the right, I have T1 cosine theta to the left. I have two one-dimensional problems. I took my vector, broke it up into components. These represent the components and the original vectors in the problem. It is now two one-dimensional problems, an x-dimensional problem and a y-dimensional problem. All right, we have done all the work on the free body diagram. We have done our coordinate system. We are ready to solve the problem. We are ready to apply Newton's laws. So, Newton's laws, net force equals 0. So what does that mean for us? Well, it means net force in the x direction equals 0, and net force in the y direction equals 0. Newton's laws is three-dimensional. We have to turn it into one-dimensional parts. This was a second law problem. Hopefully one of these would be MA and one of these would be 0. But this is a first law problem, so they're both 0. Now, applying Newton's laws actually means to follow the set of instructions that is here. And the set of instructions says, add up all the forces in the x direction, taking into account their direction, and set that equal to 0. That's what the set of instructions says to do. It's not an equation. It's a set of instructions. Follow the instructions. So in the x direction, I have T2 to the right, so it's positive. I have T1 cosine theta to the left, it's negative. So I am setting this direction to be positive and this direction to be negative. And I'm setting those equal to 0. Going to do the same thing in the y direction. I'm going to set upwards to be positive and downwards to be negative. So I'll have T1 sine theta, positive, minus weight equals 0. So what I have done, I have created two custom relationships that might be used to answer the question or might be used to study the arrangement. Either way, this is all Newton's laws can do. I am at the end of the problem now. That is what applying Newton's laws will do. It'll generate relationships. Now, you might be able to use that to do something else. You might not. But at this point, you're done using Newton's laws because they will give you this. You have to decide if this has meaning. Now, you were asked actually a question. And let's see if we can solve the question using Newton's laws. The question was, find the size of the tension in terms of the weight. Well, this one is not going to be very useful to me, is it? Weight doesn't even appear here, so I don't think I can do anything with this one. But this one has weight in it. Pretty sure I can solve for the tension in terms of the weight. So, let's do that. T1 sine theta equals the weight. So T1 equals weight divided by sine theta. All right. No big there. That's only one of them, though. I need to find the other one. Pretty sure I could do substitution to find the other one. Do you guys see what I see there? That I have a way of finding T2 in terms of T1. So I'm going to go ahead and do that. I'm going to say that T2 equals T1 cosine theta, which means it equals weight over sine theta times cosine theta, which means T2 equals weight times cotangent theta. Some of you know what that means, some of you don't. But cosine over sine is cotangent. If you don't know that, that's okay. There's nothing wrong with leaving it like this, but this is harder. There's other ways to write it. You could write this as weight divided by tangent. That would be true too. In fact, I like that one better. I know there are some people in the room, though, that don't know this. So don't be shy. You should say so. But if you don't know that, then please know it now. Sine over cosine is tangent. And I know there's a bunch of people who don't know why this is true. And I didn't know that until earlier today. So remember, sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. So if I multiply this by hypotenuse over hypotenuse, I get opposite over adjacent, which is tangent. That's why sine over cosine is tangent. So that's what I know. I know that T1 is the weight divided by sine theta. And I know that T2 is the weight divided by tangent. Now, here's what I really want you to understand. There's no numbers here. Even though I said that the mass of the box is m, I don't need that for this, because I was allowed to put this in terms of the weight. But this tells you stuff. And for those of you who don't see what it tells you that if you're going to the sign store and you're going to buy cable for your sign, and you buy cable that is strong enough to lift the sign, then the cable's going to break. Because no matter what, the tension in the cable is going to be more. No matter what, the tension in the cable is going to be more than the weight of the sign. The only way it won't be is if you make the angle 90 degrees, because sine of 90 is 1. If you choose any other angle, the tension is going to be greater than the weight. Now, you might not see that that's important, but plenty of people have been killed by falling signs because the people who installed them didn't know what they were doing. So maybe the bolt you're using, or the thing that connects to the ceiling and the wall, isn't strong enough. That's why they give you the ratings for these things, so you don't make this kind of stupid mistake. But plenty of kids have been killed on swing sets because they chose ropes that couldn't actually support the swinging weight of the kids. It comes down to this kind of stuff. So, this is the static problem that has to do with the sine. Hopefully you have all of those things down, but you also have all the things that you need to solve your own version of this. Is that okay? There's something else that's evident here. You can't actually hang the sign if T1 is horizontal. Do you see that? And if you don't, come on people, stay with me. I know you're hungry. But if theta is 0 degrees, then the tension would have to be infinite in order to hold the sign. So if somebody asks you, can theta be 0? You should be able to say no, and you should be able to say why. And not just because this is infinite, You should be able to say it can't be 0 because if you look back at the picture, if theta is 0, that means that the tension is just sideways, and there's no part of the tension that lifts the sine upwards. So it's impossible. All right.